continuing our discussion of how to make Muppet models better by talking about fine-tuning and adaptation. Let's begin on a depressing note. You are not OpenAI, but you can still optimize your models. You just can't do it in the same way that OpenAI does. And there are several different approaches for doing this. We're going to talk about those today. Distillation, adaptation, and other things that we've talked about will come up again here today, including quantization and prompting. The good and bad news is that Muppet models have grown 100 times in their compute requirements in just a few years, and they're continuing to do so as the hyperscaling wars continue. One way to fight against this trend is to distill your models. You don't need a model that does everything. You just need a model that does the things that you care about. So find the things that you care about, take the insights and world knowledge from a giant model and distill it down into a model that you actually can use on the machines that you have. One of the first examples of this was Distilbert, which did exactly this. You had some teacher model, and you train a smaller model to mimic the teacher model. Not just in getting the same answers, but trying to match the distribution of the outputs. And this ended up giving much better results. Rather than just having the loss function as being, did you agree on the label? We actually want the cross-entropy distribution over the distribution over possible outputs to match. And particularly when the distributions are very peaky, you might want to go a step further and actually use a higher temperature to capture the details of the distribution so that it doesn't just turn into the, did I match the argmax or not? I want to actually capture what's happening in the label distribution. When you have access to the full model that you're trying to distill, you can go even further. Rather than just taking the final outputs, you can try to match pairs of layers. So throw out every other layer, make it so that when you merge layers 3 and 4 from the original model into your smaller model with half as many layers, your new combined layer is doing the work of both layers 3 and 4. Oftentimes there's duplication and redundancies in these large Muppet models that you may not necessarily need. It was necessary for training, but when you deploy it, maybe not so necessary. In addition to distillation, there's also adaptation. So distillation works when what you're trying to do is simpler somehow than the full power of the underlying model. But sometimes you need that power. Sometimes you need to keep the full model around, and you need to adjust it for your purposes. But you can't fine-tune 70 billion parameter on your own. Part of the problem is that if you fine-tune, you need to store all of the parameters, and this isn't always possible. And not just store them, you need to do backpropagation over the full model. So what's the alternative? Let's zoom in a little bit. And so at the heart of all of our models are a bunch of neural networks. And so our feed-forward layers, our key-value lookups, all of these are just neural networks parameterized by some matrix. And when you do backpropagation, when you fine-tune a model or update it, then you're changing those parameters. But maybe there's a way that you don't have to change all of them? And so the big idea of doing adaptation is that you add this additional gadget, and we'll call this gadget an adapter. And instead of doing backprop on the weights W1, we're going to create a W1 prime where we keep track of the delta. And maybe we can represent that delta with smaller matrices. Now, of course, the delta needs to be the same dimension as the underlying parameters, but maybe we could make A and B a matrix multiplication of a tall skinny matrix and a short fat matrix. If you do that, you can get all d-squared tokens. This is called a low rank approximation of W1. So let's say that the original matrix, W1, was a D by D matrix. And so I had big D before as the delta, here's little d as the dimension. So then we have a D by R dimension for A, and then we have an R by D dimension for B. If you did a full update, you would need a D squared matrix, but now we just need to add R to D to the total. So does this work? The short answer is yes. You're able to update models to do better on a task that maybe it hasn't seen before using a lot fewer parameters, and sometimes it wins over doing full fine-tuning. And I bet if they tried harder, they could have gotten the fine-tune to win, but you can get a bigger bang for your buck by doing it like this. What's the right rank? It depends on how hard your task is and what the weight matrix looks like. So this is really an empirical question. You can't answer it a priori, but you can try out different sets of ranks and see what works. And for example, in this task, trying to create SQL queries or doing natural language inference, it seems like rank 8 works pretty well. There is some theory about this, but it's all in terms of the neural network that you're trying to represent, rather than the data, because we don't have good theory about mapping data to the underlying network that needs to represent it. But if you can represent the new function f hat with a neural network of a particular width and depth, you can use that to decide what your rank is going to be. So if you have a simple enough function that you're trying to represent, you can do it with an adapter. 4, we talked about quantizing a whole model. Can you also quantize your adapters? Because this can get pretty big, because we weren't talking about distillation. We're adapting a whole darn model, and those things can be pretty big. Could you quantize that and take up less space? The answer seems to be yes. This paper from Ten Detmers et al., you can use the same tricks that we talked about for quantizing a whole model by not using a full floating point representation for your adapters, but by using a much smaller number of bits to represent the adaptation weights as integers. This works because, like for quantizing a model, you don't need to represent the full range of the floating point that's possible on a standard computer. Most weights are in a relatively narrow range, and we shouldn't use the full range of floats for our integers. We should restrict the range and map that to our integers. And so nothing new here. We already talked about quantization generally, but what's different about adapt? Oftentimes there are outliers and we need to represent them. We don't want to use all of our integers for this. We should have a budget. So if we expanded our range out to encompass them, this wouldn't work very well because we'd have a bunch of collisions where we actually need higher fidelity to represent the meat of the distribution over the matrices that we need to represent. And you can't just forget about the outliers, because a lot of the neat stuff that happens in Muppet Models happens because of the outliers. The heads that have these outliers are actually really important for getting low perplexity, to modeling the data well. The neat thing that QLoRA did that goes beyond what we did for standard quantization of models, where you have regularization that better accounts for the weights and keeps them in a narrow range, is that, let's look for the heads with outliers and handle those separately. Just have a separate term that handles the outliers and represents them in full precision. And then for the things that aren't in outliers, we handle them with integers, 8-bit integers. As you do the LoRA adaptation, having these outlier features works a lot better than using a standard 8-bit method, without inducing a lot of extra computational overhead. Because of computational complexity, there's a lot of stuff that you can't do with the largest models. Sometimes they're locked behind an API in a black box, and you can't do anything, except trying to do prompt optimization, and if you do that, again, you should use something like Dispy, not do it by hand. But sometimes, even when the large models have been open sourced, you can't do full updates of the model. It's just too big. You don't have the resources to either store the parameters or to do the computation. Adaptation provides an alternative. You compute low rank deltas to the parameters that you can store, that you can compute, and you can change the models more efficiently. QLoRA lets you be even more effective. By quantizing the low rank matrices, you can do fine-tuning even on laptops and on machines without GPUs. Muppet models are great and they can do a lot of things, but they don't always do exactly what you want them to do in the way that you want them to do it. But hope is not lost. There are lots of opportunities for you to still change the models and to get them where you want them to be. Thanks for watching this video. I picked out another video that you could watch up here. If you want to get more context for the videos, check out this link or the link in the description. It gives you readings, programming assignments, and other things that might be more helpful. Finally, help me out and help other people find this content by providing a big gradient to the recommendation algorithm. Like the video, subscribe, or leave a comment down below with mistakes that I've made, newer research that has come out, or just tell me about where you are in your journey.